Hello again, everyone. Before we go too much farther with our web servers, let's stop for a minute and take a look at DNS, the domain name system, and make sure that we understand how human recognizable names get transferred into IP addresses, the numeric addresses that computers use to talk to each other. We'll look first at how IP addresses are structured, then we'll go into host names, and finally, the basics of how DNS works. In the next lecture, we'll look at how we can use DNS, but not really get into the details of managing a DNS server. Computers on the internet talk to each other using IP addresses. IP is short for Internet Protocol, and an IP address uniquely identifies a computer on a network. Each IP address is a number, a very large number as we're about to see, and rather than trying to manage these huge numbers and keep sense of what they mean, notation actually breaks the bits of these addresses up into smaller pieces that are easier to understand and easier to work with for network administrators and really anybody that has to deal with this stuff. Currently on the internet, both IP version 4 and IP version 6 are in use. Internet Protocol version 4, or IPv4, has been around since 1983. It uses 32-bit addresses, and I'm sure that the 4.29 billion addresses that this address space handles was far, far larger than anyone thought back in 1983. After all, it was in the 1980s that Bill Gates said that a PC computer would never need more than 640K of RAM. That turned out to not be true, and the public pool of IP addresses in the IPv4 scheme was exhausted February 1st, 2011, when the last network blocks were assigned out from where they're assigned from. And the IPv4 notation uses 4 sets of 8-bit numbers to represent that 32-bit address. So 172.116.254.1 is a good example, because an 8-bit number is 0 to 255. So that's just taking those 32 bits and breaking them up into 4 8-bit sections. Now, IP version 6 has been around since 1998, so you may be asking yourself why the switch wasn't made. We've known for a long time that we're going to run out of addresses, but rather than switch away from IPv4, what happened was people started using private address spaces, reserved address spaces behind firewalls, and it dramatically reduced the number of IP addresses that actually were needed on the internet. This is still going to be a problem, and it keeps getting worse every year, but it is going to slow the conversion to IPv6. IPv6 has a lot more room. It has 128 bits of address space, and that provides over 340 trillion addresses. I read somewhere that that is enough addresses for every atom on the Earth, and then 100 more Earths. Now, there's a little bit of confusion and interpretation about that particular quote, but needless to say, there are a lot of addresses in this space. Now, the IPv6 notation uses a set of 8 16-bit numbers, and those are represented in hexadecimal digits. So digits that instead of going from 0 to 9, go from 0 to F, where F is the equivalent of 15 in decimal. So you see an example IP address here that shows the notation that way. Now, when you have an address for a computer, that is the unique address on the network for that computer, but it has a little bit more meaning than that, because the way that network routing works is that IP addresses are broken up into networks and then individual nodes or hosts on that network. Now, we use the word nodes because a host can actually consume more than one IP address. That gets into a little bit fancier configuration. So the better choice of word is node, although host is a good name too. In any case, you'll hear the term subnet mask, or maybe net mask, and that defines how many bits of the address, starting from the left or from the highest order bits, represent the network. Everything after that, on the right-hand side of the IP address, or the lowest order bits, represents the host or node ID. In IPv4 255.255.255.4, the notation can either be 255.255.255.0 or /24. Both of those indicate that the first 24 bits, the first three numbers of the IP address, are the network, and the last number would be the host range within that network. So given an IP address of 172.16.254.1 and that net mask of 255.255.255.0, we know that the network is 172.16.254.0 /24, and the node is 1, where those node values can go from 1 to 253 for reasons that I won't go into here. This isn't a class on networking and IP addresses, but I want to at least introduce the concepts so that we understand what these IP addresses are when we start making references to them by tying names to IP addresses. Now, IPv6 also uses subnet mask to separate networks from nodes, but the networks can be much, much bigger, and it's not uncommon to have a subnet mask that actually gives about 64,000 addresses on a network. In fact, that's kind of become the norm. So again, because the address space is so big, that providers are just starting to hand out huge networks to even small customers like home users from Comcast or some of the other cable providers. Now, names are much easier to remember than numbers. When I was a kid, I knew everyone's phone number. I had them all memorized. I knew my phone number, at my parents' house. In fact, today, I could tell you my phone number at my parents' house when I was a kid. In fact, today, I could tell you my childhood phone number faster than I could tell you my cell phone number. I have to stop and think about that one because I don't give it out anymore. We always share that electronically. And we don't have numbers stored in our phones. We have people's names stored in our phones, and we don't care what the number is once we get it. It's just a given that names are easier to remember than numbers. And even before IP came around, interconnected computers were always referenced by name, and there was always a way that the computers could be told what those names meant. Now, simple IP name lists can be stored in a host file. And in fact, back in the early days of ARPANET, there was a master host.txt file that was updated manually, and the way that you got added or changed in that file was you had to make a phone call during normal business hours, and then someone would edit the file that everyone used to keep track of where the hosts were. As networks grew, obviously a distributed naming system was needed, and that's when DNS came along. DNS is based on the concept of domain names. Domain names provide simple identification labels that indicate who owns or controls a resource. The Internet Corporation for Assigned Names and Numbers, ICANN, is the group that manages the top-level domain on the Internet. All domain names on the Internet are connected in sort of like a tree shape. And that tree starts with the root at the top instead of the bottom, and then the branches go down. Here's a slide that shows that, and you see the top-level domain here, and that authority is the root name authority. And then branching down from that, we have other layers of authority that branch down further and further and so on. So this could be, this is the top of the internet. This could be .com or say .edu. And so you have hfcc.edu down here, which is the Henry Ford College domain name, and the resource record for a name server says that name server is down here, and down in this space are the domain names or the host names that we control within our own domain for the college. Now, the syntax for a domain name is fairly simple, and you've seen them for many years now. But it's important for this class to understand how these parts work and how they fit together, at least a little bit. So the syntax is pretty simple. It's one or more parts separated by dots, such as example.com. The rightmost portion of this domain name conveys the top-level domain. So if you have a domain name of www.example.com, the top-level domain is com. or often referred to as .com. And then hierarchy, as you move further left, you get more and more specific, and the ownership of that is more and more specific, or more and more individualized, I should say. Now, a host name is any domain name that has at least one associated IP address. So this web server example at example.com, those would have host names, or probably have host names, while .com itself doesn't have any IP addresses associated with it, so it would not be considered a host name. Top-level domains are the key to the DNS system on the internet. Back in the 1980s, when this first got created, domains were divided up into two groups. First, there was a group with country codes, and most of those country codes were based on the two-character territory codes that were an ISO standard. So US for the United States, UK for the United Kingdom, .de for Germany. You're probably familiar with some of these domains, at least in some way. There were also 7 generic top-level domains when the system was first developed: .gov, .edu, .com, .mil for military, .org for nonprofits, .net, and then .int, which was for international connections. And it's used, but it's not used very often. It'd be very rare that you would actually go to a .int website, but it's used for connections, sometimes transcontinental connections, between countries around the world. The system expanded since the 1980s, and a few years back, we started having more and more top-level domains added. Since 2016, there are now over 1,000 live generic top-level domains. That's quite a few to keep track of. Now, even before we started adding all those generic top-level domain names, some of the countries involved started selling out. Probably one of the best known now is .tv. You see a lot of websites for TV shows or television networks that have a .tv domain. That's actually the country code for Tuvalu. And then things like Bitly and some of the other domains that use an ly at the end, that's Libya. And then finally, TO for Tonga. That's just 3 examples. There are actually many of the domains, country domains, that have sold out and commercialized, and rather than just being websites for within their country, they'll sell domains to just about anyone that can do that. The .us domain is actually similar as well. It used to be locked down and pretty well structured, so that the second level of all US domains was the state code. So for example, mi.us, and we see that a lot with K-12 or community colleges, especially back in the day, where a Michigan school district would be in the k12.mi.us domain, or community colleges like Henry Ford was henryford.cc.mi.us. When Henry Ford College first got on the internet, that was our domain name, and that was how you accessed all of our stuff, was through henryford.cc.mi.us. For a while, community colleges weren't allowed to buy EDUs. And some community colleges had purchased an EDU before that rule went into effect. They were allowed to keep them, but no other community colleges were allowed to join the EDU domain until several years later. Now, having this structured worldwide system wouldn't mean much if there wasn't a good way to control it. And control is handled by the Internet Assigned Numbers Authority, IANA. And they maintain a list of all the top-level domains in the root zone database. DNS, for that very top level of domain names, is served by 13 clusters of root name servers around the world. Those servers are now known as a.rootservers.net through m.rootservers.net. That doesn't mean there are only 13 servers. Each location of those 13 locations has a whole cluster of servers for fault tolerance, backup, and support. And whenever you start up a new DNS server, they usually start up with this list unless they're using some other server as a forwarder. Here's a quick look at that root name server list. and you'll see that the addresses, locations, and operators are scattered all over the world. So that even though there's a centralized control of that top level domain, the actual ownership of the servers and the operation of those servers is spread across a pretty wide variety around the world. This is part of what protects and makes sure that we keep a free and open internet. So how does all this work? Well, it's kind of complicated and there are a lot of details, but here's the rough idea. An individual computer, like the one you're sitting at right now to watch this video, needs to get to a web server. So it's going to request the address for the name of the web server that you're trying to go to. This will go to your DNS server. Now, if you're on a corporate network or on the college network, it's going to be one of the DNS servers that that corporation or the college maintains. If you're at home, then chances are you're using DNS provided by your internet provider, unless you've manually configured something different, again, like Google's servers, to use instead of using the ones provided for you. Now, these DNS servers generally cache, so they don't have to look up everything every time. So how does this work? Well, rather than read you this whole slide, let's just take a look at an example. Say you want to go to www.example.com. Your DNS server is first going to query the root name server for .com. Now this is cached, so any other .com website that you want to go to, or anyone else who uses that DNS server wants to go to, it will have the .com name servers cached, so it won't have to go look every time. So once that DNS server knows where the .com name server is, it will go ask it for the name server records for example.com. Once that information is returned, now the DNS server can query the example.com DNS server and get the host address for www.example.com. Finally, that returning address is sent back to the computer that requested it. That's a lot of jumping around through name servers, but especially once caches are warmed up, that lookup is very fast and just a very small fraction of a second. So most of the time, you don't even notice that this is happening. It used to be a big deal back in the early days of the internet when connections were a lot slower and every byte going up and down across a modem mattered. But with today's internet speeds, DNS lookups really aren't a big deal as far as performance goes anymore. That's the basics of DNS. In the next presentation, we'll get into more detail and make all of this a little bit more practical.